Welcome. This is the fourth video in a series that I've designed so that you can self-evaluate yourself relative to some key skills that you need to have for good performance in mechanical engineering classes. What does good performance mean? Well, on the short term, that means you're going to get a good grade in class as long as you're well prepared. And you work hard within each class. Now, on the longer term, good performance means that you're training yourself to become a solid practicing engineer. And the topic on this one is dealing with the quadratic equation. And I hope that that's familiar to you. We will go over just a little basic example problem of the level to which you need to be familiar with dealing with the quadratic equation. So let's go ahead and get started. I want to look at your self-preparation for problem solving where the quadratic equation is involved. And so the expectation of the mechanical engineering faculty and staff is that you need to be able to find the roots of any second order polynomial equation. And so you might say, well, I feel pretty good about that. I might have trouble with a third order polynomial or fourth or fifth order. Might have to go to some software package to do that. But I think on the second order, I think I could do that by hand. And so that's what we want to talk about. It's my hope that you are familiar enough with the quadratic equation to set up and solve find the roots of those equations basically by hand on pencil and paper. Okay, so here's what we commonly observe in our various courses, classes, homework problems. Typically, we find a mathematical model for our situation in this particular form: ax squared plus bx equals d. And that's a little different maybe than what you covered in math class. It certainly was in high school and in college math for me. So, but typically in engineering, we end up with an equation that looks like this, where A and B and D are numbers, and we're trying to find a value or two values for X. Okay, and so that's second order polynomial equation. We're seeking to find X. And so what values of X makes the left-hand side exactly equal to the right-hand side, which is D. So that's usually the answer we're seeking in our homework problem. Well, so then we dust off the cobwebs and we think, I've got something like this that I studied in math class, okay? But I remember the general form we had in math class looked like this: ax squared plus bx plus c equals 0. That's the second order polynomial that we sort of learned in math, whether it was high school or college math. Okay, and so let's review the definition of the roots of an equation. So there's going to be two roots, two values of x will satisfy this equation. In other words, the left-hand side exactly equals 0 to equal the right-hand side. Okay, the values of x are called the roots of the second order polynomial. Okay, and so then you're dusting off the cobwebs. Say, yeah, I remember, if I've got my polynomial equation in this form, I should be able to rattle off the quadratic equation. X equals, basically a formula, is negative b plus and minus the square root of b squared minus 4ac, all of that numerator divided by 2a. Okay, it is my hope that you've got that in your head. It's my hope that you've got that memorized. If not, it's okay. You can go to Wikipedia or an old math book of yours and refresh your memory on that. So I recommend you have it in your head, but not necessarily now. Calculating X looks easy, but the devil's in the details. And I hope you remember that there are some complexities associated with this, right? And I'll pause it. Do you remember what those are? What's the complexities of this formula, this quadratic equation used to find the two roots of that general second order polynomial? What's the complexity there? Okay. So of course there will be two roots. How do you know there'll be two roots? Well, in our quadratic equation, we're adding this value and subtracting this value from b before we divide by all of that by 2a. Okay. And now we're getting to a little bit of the devil in the details. Understand what the discriminant is. So that term b squared minus 4ac, that term that's underneath the square root sign, the radical, that's called the discriminant. And its value, it's the value of b squared minus 4ac determines whether the two roots of the equation are either going to be real numbers or if they will be complex numbers involving an imaginary number. Okay. And that's because you have to take the square root of b squared minus 4ac. And so what happens when you evaluate with your calculator b squared minus 4ac and you get a negative number for that? You sure can't take the square root of that on your calculator. Okay. Can't take the square root of a negative number on your calculator. Okay. And so you remember this, when b squared minus 4ac is greater than 0, it's a plain old number, there will be two real roots to the solution. Okay. When b squared minus 4ac exactly equals 0, there'll be two identical or repeated roots. There's two roots, but numerically they're exactly the same. Very unusual. Or situation where b squared minus 4ac is a negative number. Well, there will be a complex conjugate pair of roots when b squared minus 4ac, the discriminant, is negative, because you end up with I. You remember the square root of minus 1 is I. Okay, so this slide totally only depends on when you have b squared minus 4ac is less than 0. You have a complex conjugate pair of roots, because you'll pull out b squared minus 4ac is a negative number. You'll pull out I, okay? And so you have negative b plus I times some number, all divided by 2a. And the second one will be negative b minus I times some number, all divided by 2a. Okay. All right. And so there's the conjugate roots. And so notice here, so the result, when b squared minus 4ac is a negative number, very straightforward. You're going to pull that I out, take the square root of minus 1, pull that out, and then just take the square root of the absolute value of b squared minus 4ac, and there you've got your complex conjugate pair. All right. Now, there are some real-world implications of the real roots for quadratic equations. So there's our form, okay? And so recognize that let's look at the situation where we have two real roots. For right now, let's forget about that complex conjugate stuff. Say we have two real roots. There are many situations in which one of the roots is a positive number and one of the roots is a negative number. That's very common when that happens mathematically. Okay, let's look at the real world. Now let's say we're practicing engineers, and our particular problem, we're trying to solve for a velocity or a mass or a volume or a temperature or a pressure. So what I want to suggest in the real world is that those variables can't take on a negative value, okay? Particularly mass, volume, temperature, and pressure. I think you could argue velocity, if you had assumed velocity going that way, if you get a negative number, the velocity is going the other way. But in the real world, you're not going to have a solution where the mass is a negative number. You're not going to have a negative volume. You're not going to have a negative temperature, nor will you have a negative absolute pressure. Okay. And so talking a little bit about the details here is that in many situations, you're only going to be seeking the positive root and you're going to ignore the negative root. All right, so let's do what I want to do is here's an example. An engineering model results in the following relationship: alpha times t squared plus beta, Greek letter beta times t equals d, a number. Now, this is the numerics here are taken from a real honest to goodness thermodynamics problem where capital T is temperature in degrees Kelvin. That's an absolute temperature scale. So that number has got to be, the result has got to be greater than 0 to be a realistic answer. And the coefficients are given: alpha, Greek letter alpha, 0.7963, beta, 2016, and D is a large number, 622,081. All right. And the question is determine T, the realistic temperature. All right. Well, let's look. So let's look at going through the numbers here. Okay. So here's our given information. Okay. Let's rearrange our mathematical model to fit the quadratic equation form, ax squared plus bx plus c. Okay. So that's going to be our first step. So there are going to be 2 roots to the quadratic equation. Okay. All right. And so C, so here we go. Alpha is A, 0.7963. Beta is B, 2016. And C is negative D, or negative 622081. Okay. C is a negative number. All right. So now what we're going to do is we're going to dissect. So should be able to go right into a calculator and get a result, but let's study the numerics before we go to the calculator. All right, let's look at the denominator first. Is the denominator going to be a positive number or a negative number? It's going to be positive, 2a. It's a positive number. Next, let's look at that b, the leading term in the numerator. The numerator starts with a negative number. It's negative b, so this is a negative number. We're starting out with a negative number, and we're going to plus and add and subtract some number here. Okay, okay, what's our discriminant? It's bigger than 0 because b squared obviously is a positive number, minus 4ac, minus 4 times a positive number times a negative number. That's going to be a positive number. So the square root of a positive number plus even more, this is going to be a positive number. So we've got 2 real roots by looking at the discriminant. Okay. So looking ahead, which root will we want to pick? We're starting out with a negative number. We don't want to subtract more from it, do we? We don't want to end up with a negative number because that doesn't make any sense. We're looking for a temperature T. So by process of elimination, we're going to pick the positive root and ignore the minus sign. We're going to pick the positive root. Okay. There's our practical conclusion. We need to determine the positive root for x because the negative root is not realistic for this particular engineering situation where we're trying to find a temperature. All right, so we're going to do the math. We're going to jam in our numbers, okay? And we come up with 278.04. So we will report in our homework problem, we will report the temperature is 278 degrees Kelvin. Okay, so that's a real world example in a real world thermo problem where we had the quadratic equation and we needed to solve for temperature. We realized that there was a positive root and a negative root, but in the real world, there's only one answer made sense. And of course, you put that on your solution and you could discuss, but it's probably best just to leave the negative root alone. Okay. Oops, excuse me. I'm sorry, I got ahead of myself. Pardon the blackout. So let's recap. What do you think of that? I would say it's 99.9% sure that you have heard of the quadratic equation. Okay. And we don't use the quadratic equation a great deal in thermodynamics, but there are other courses such as automatic controls that uses the quadratic equation a great deal in mechanical engineering. So it's my hope that you have a working knowledge of getting the roots of the quadratic equation. So I'd say you should feel pretty good about it. Maybe go to, if you need some brushing up on it, go to Wikipedia, go to the Khan Academy, and brush up on that a little bit. If you need a lot of brushing up, then go to your undergraduate advisor and say, look, I think I need a little more remedial guidance on solving the quadratic equation. And I think you and your undergraduate advisor could work together to maybe set up some help in a different department other than mechanical engineering, because of the pace at which we run all these courses. There would be an expectation that you have a working knowledge of what the quadratic equation, solving second order polynomials, is all about. So that pretty much gets us up to speed, and it's a quick review of the quadratic equation. And I think that with that little review, I think you should be pretty well versed in biting off problems within mechanical engineering that involve the second order polynomial. So best of luck to you, and best of luck for very good performance in all your classes.